All right, so part two of this general union and intersection lecture is here. We're continuing to prove parts of this theorem. I've already written the next part on the board. This is called enlarging the index set. And let's just think for a moment about what the statement is saying. Now there's going to be two index sets, capital I, capital J. I is a subset of J in this situation. That's what we're about to assume. And what it says is if you take the union of a bunch of sets, the ones coming from capital I, and then you throw in even more sets, coming from J, indexed by J, well, that's just going to make the union bigger. If you take the union of even more sets, you get a bigger result. All right, so hopefully that's intuitively plausible. And then on the other hand, if you do an intersection, okay, if you intersect even more sets than you started with, well, then you're putting more conditions on the members. They have to be in everything. So that's going to produce a smaller answer than what you get if you just took the intersection of, the set coming from capital I. Okay. Anyway, so this might be a little strange that the J and the I got reversed here. But if you're not sure about that, well, the proof will reveal why that's got to be what you do. So let's prove that. All right, and again, it's practice with all the proof techniques we've ever done, starting in this case with an if-then. Okay, that's the overall structure of this statement is an if-then statement. So to start the proof, we'll just do a direct proof. Assume I is contained in J. And then we'll prove this whole thing. Which again, just to save board space, I won't recopy it all. A full proof would recopy, but one reason I'm not is because the goal is an and statement. So we're immediately going to have to launch into a two-part proof anyway. Part one, prove the first thing. The union over I in capital I is a subset of the union over J in capital J of these A's. Again, all these A's have been fixed in advance. I is fixed, J is fixed. Index sets are non-empty, even if I didn't write that on the board. Okay. So how do we do this? And again, every time there's this little pause, and you're saying, well, and you're going to be writing these lines of proof even before I say them, or at least thinking them in your mind. This is another subset statement, so we're going to do another one of these subset proof templates. We're going to fix that arbitrary x, choosing x as my letter. We're going to assume it's in this left-hand side. We're going to prove x is in the right-hand side. And then what else can we do? We have to expand definitions. Assumed, what did we assume? And you're all thinking, there exists I in I, X is in AI. That's the definition that we memorized. And in this one, it's the same kind of thing, but we're proving an existence statement with a different index set, like that. Let me use green for an assumption. Circle that in green. This is a little I here. And red for a goal. I really like this theorem and proof as a way of hitting on this main theme about the contrast between assumed existence statements in this case and a to-be-proved existence statement. In this proof, we know this. We need to prove that. Therefore, the two statements are treated entirely differently. Okay? We're not going to choose an I, for instance. Why? Because this isn't the goal. We are going to choose a J, because that is the goal. Okay? And maybe just to be even more explicit about, we haven't always been so explicit about how you use an existence statement that you've already assumed. Let's even get rid of this variable, just be very explicit and say, what does this mean? there exists an I, that means there's a particular index. We know this. We've assumed. We assumed there is a particular index. We don't control it, by the way. We don't choose it or have control over it, but we know it's out there. Let's call it I naught. And what do we know about that I naught? We know it's in I, the index set, and we know it satisfies this statement. X is in A sub I naught. Okay. And there's a fancy word for what I just did. It's called existential instantiation, or the inference rule for exists. You don't really have to worry about those phrases, but the point is, a constant comes to you not under your control, not chosen by you, but it has the properties. It's in I, and this holds. Okay. Now, moving over to the ret statement, we have to choose a j. Now, because we're proving it, it's our job to pick the j, and we can pick anything we want as long as it works, to prove it works, right? Well, having just said this, I hope you're not going to be utterly shocked when I choose j to be I naught. Why? Because right here, we know that x is in A I naught. So x is in AJ because x is in A I naught. Now, this isn't the end, though, because when you're doing a proof of an existence statement, you have to also show, some people are forgetting this in some of your proofs, that the thing you pick is in the universe it has to be in. It's got to be in capital J. And that you might worry about for a second, because look, that's not what we assumed over here, okay, for this thing I just chose. It's in I. It's supposed to be in J, though. And that's where you go back up and remember, wait, we also, at the very beginning of the proof, assumed that I is contained in J. Okay, so that's key. Since capital I is contained in capital J, and I naught is in I, well, by this known subset fact, if you have something in the small set, it's also in the big set. So I naught is in J, and that's what we chose little j to be. And that is essential, that the proof must discuss that and use this I subset of j. That's the only place the assumption has been used so far, part one. Okay, and it's not true without that. You just had random sets I and j. All right, so anyway, so that's that. Okay, so we've done that one. Part two, and again, the really crucial thing is the interaction. Known existence statement, goal existence statement. And they're treated very differently, but of course, one of them helps you do the other one. Part two, let's prove this with the reversal of the two index sets. All right, and let's have it's another subset proof. So we're going to do the 3 lines with maybe a new letter just for safety. Maybe call it y. Fix arbitrary y. Assume y is in the intersection of the AJs, j going through the index set capital J. Prove y is in the intersection of the AIs. And I'm really hoping that's the camera still. I think it can see that. Hopefully that's true. This line represents as far as the camera in principle goes. All right, and so we get to expand definitions here as well. But now it's the intersection. So now we've assumed that for every j in capital J, y is in AJ. And we have to prove that for every I in capital I, y is in AI. Once again, I'll circle things with these colors to try to keep track of the assumptions in green as they get expanded, and the goal in red to be proved. And here too, the main theme is coming back to us. We have now a known universal statement, which gets used in one way, and a to-be-proved universal statement that gets treated in a very different way. Here we have the inference rule for all. We can choose J's, whatever we like, as long as they come from capital J, and we get some information, lots of information, because it's for all. Here, though, let's keep going with the proof. To prove for every I and I, we have to fix an arbitrary index. Let's call it I1, just so it doesn't look like this guy, although we could reuse I0, but just to avoid any chance of confusion, I'll make a new constant here. Fix an arbitrary index coming from capital I. That's part of the assumption that's when you're fixing, you're allowed to do that here in this proof of the universal statement. And we have to prove, the new goal is that Y should be a member of A sub I1. That's an easier goal. We've gotten rid of one of the symbols. All right, so how are we going to do that? Well, we've got to somehow use this assumption. But this assumption is a known universal statement, but only about things in capital J. Okay, so let me call this assumption, let's call it double star for reference. So in double star, by inference rule for all, I claim that we can let or choose or substitute, whatever word you want, let J be I1. And there's a crucial thing we have to worry about here. I almost said you just let J be anything you want. It's anything. Because it's a for all statement, but that's not quite true. It's only anything in J. Capital J. Okay. So when I just cavalierly do that, how do I know? So, because look, I1 comes from I. All right. So here's the crucial point where once again we have this I subset J thing. We need that because I is contained in J and I1 is in I. We see that I1 is in capital J. So this choice is allowed, okay, but only because of that. All right. Having said that, however, we get from double star that Y is in A sub Y1 as needed. And if you look closely, if J and I hadn't switched places here compared to where they started with the J on this side and the I on that side, if this had been an I and that had been a J, this proof would not have worked because this wouldn't have. I1 would have been in the wrong set. So that's somehow explaining why that thing got flipped around. But I guess that's it for that proof, isn't it? I think we've finished that now. We've done both parts. All right, and we're doing great on time. I think 38 plus 13. Let's do one more. Maybe I'll let you look at the set builder stuff on your own. That's not so hard. But let's try to crank through this one last proof. These proofs are a little bit intimidating, but they're just so valuable for understanding quantifiers. So that's why I'm doing them and trying to explain them in great detail in this video. This is part of part H, part 2 of part H. I'll just write it. Here we're going to have, again, we're going to have two index sets. We're going to have AI coming from capital I coming from capital I. And that, we're going to intersect those, and we're going to intersect that with another intersection over J and J of AJ. And the weird thing is the answer you get is another general intersection, but the new index set is actually the union of I and J, not the intersection, which may or may not be what you thought it would be. All right, but that's what happens when you take the intersection of two intersections. You can write that as a single intersection over a new index set. Okay. So let's look at how that works. Everything is a set. So set equals is a set equality, and that's probably going to be a two-part proof. This seems too complicated to risk trying a chain proof. So let's not do that. Let's prove the subset in both directions. And I'll shorten it a little bit by just sort of saying that as an indication of what's about to happen. I'm about to prove this as a subset of that using the subset proof template. So let's fix arbitrary x. Let's assume x is in this left-hand set, whatever it may be. Some really long thing, doesn't matter. And prove that x is in the right-hand set. Okay. All right, and so just keep going. Just keep cranking through definitions until you get down to the basic stuff. Just be sure to crank through them in the right order. Like here, the first thing that has to get expanded is the individual intersection, the old intersection of two sets. So what did we assume here? We assumed x is in set number 1, and x is in set number 2. This set, that set. Which means, let's keep going, which means we've assumed for every I in I, x is in AI. And for every j in j, x is in aj. And what we have to prove, expanding, here we just have a single definition that's expanded at the beginning, is that for every k in the new index set I union j, x is in ak. So an assumption here is the and of two universal statements. Goal is a single universal statement with this universe. So keep going. So fix, we're proving a universal, right? So fix an arbitrary k in I union j. And we have to prove x is a member of ak. And when you fix the arbitrary object in the universe, the fact that it's in the universe is part of the assumption. You're not just fixing anything, you're fixing something in here. So we know, by definition of ordinary union, k is in I or k is in j. Hopefully that was an audible bell that made you all immediately say, when you have this known or statement, well, then we're going to use proof by cases. Hope that bell wasn't too loud. Proof by cases. Case 1. Assume the first alternative in the OR. And then we have to prove that. And let me just, so I don't forget, let's make case 2. Let's at least set it up. Assume the second alternative. K is in J. Same goal, but we have to prove it again. Okay. How do we do that? Well, looking in case 1, for instance, and looking back at our green statement, We know stuff, and means we know both pieces, of course. We know about indices that come from capital I. For every such index, whatever it may be, x is in AI. And look, in case 1, k is in I. So we can let I equal k. I don't think I've used star yet. I'll call it star. But I equals k in star to see, because it's true for everything, including this little k that comes from capital I. So I get that x is in a k, which is the goal. End of case 1. And then similarly, in case 2, I have a different information about k. It comes from j now. But star also contains the information that for any j and j, anything, as long as it's in j, I have that. So in case 2, I say, since k comes from is a member of capital J, we can let j equal k in star, the second half of star, to see that x is in ak. It's in aj. J has been substituted with k, so x is in ak. How about that? All right. So that's good, but that's only part 1. That's the first direction. You see these set proofs kind of go on and on sometimes. But that's the way it works. Now let's do part 2. Part 2 is this other inclusion. Let's fix a new letter, W, say. Let's assume W is in this right-hand set now. And let's try to prove that W is in the left-hand set. Try not to get too intimidated by the gigantic intersection symbols, all the symbols. Seems like a lot. You just march through them one by one, expand definitions little by little, and go from there. Here we assumed, expanding the same definition we had earlier, for every k in I union j, W is a member of AK. That was the goal in the proof we just finished, part 1. Now it's the assumption, so it's in green now. It's really an if and only if hiding underneath here. And over on the other side, again, there's an and then this expands. So we get for every I in I, I'm sort of doing 2 steps at once here, but only because we already did this step in part 1. This turns into and then you get these universal quantifiers. W, N, A, J. That was the assumption in part 1. It's now the goal in part 2. What's a new letter for W? Okay. And anyway, so now we're here, right? What do you do now? What's the goal? It's an and statement. How do you prove an and? You do 2 parts within part 2. Part 2a, let's prove the first part of the and. And in part 2b, let's prove the second part. So these are goals, so I should put them in red, I guess. The goals are universal statements. So we do that typically. Fix an arbitrary index. Let's call it I naught. I just sometimes put that subscript. You could call it I if you really wanted to, but I naught emphasizes it's one particular constant index. It's not a variable anymore. It's not changing. It's fixed. It's unmoving. It's unchanging. It's in I. It's part of what we assume right here. And we have to prove that W is in A sub I naught. How are you going to do that? Well, we have to use the assumption here, okay? And okay, so this is a known universal statement, true for every k in this union. We get information about W being in AK. Okay, I guess I want to call it double star, again, just for reference. So take k equal I naught in double star, which is allowed. You can't just do anything. So got to be something in here. But that's allowed because, let's make sure, because I naught is in I, which we know by a theorem, I is a subset of the union I union J. So this member, I naught, is a member of I union J. And this is the point where this is kind of why this had to be a union, not an intersection, for this step to work. I is not a subset of I intersect J in general. Okay. But that's true. And so because it's in the universe of the known for all statement, I can make that replacement and conclude safely that W is in, well, K, but I just replaced K by I naught. So I get W is in A naught, which is the goal of part 2A. So I'm done with part 2A. And then part 2B is going to be virtually the same. We still have to do it, though. Fix arbitrary J naught in J. Prove W is in A J naught. And of course, you're not going to be shocked that this time you can use the known universal statement over and over and over again and use many different Ks. Now we can take K in this part to be J naught. Well, is that really okay? That's okay, that's permitted, only because that J naught is in J, capital J, which by a previous theorem on subsets, capital J is a subset of I union J, and therefore J naught is in I union J, which is the universe to which this known for all statement applies, and we therefore get that W is a member of A J naught, which was the goal here. Good. So part 2B is done, part 2 is done, the whole thing is done. We're done with that. 38 plus 27 is 65. All right, 5 minutes. Let's just, for 1 or 2 more minutes, let me just throw the set builder definition on the board. I'll let you read on the handout in the book for more details of that. All right, but just quickly, just so we have a little bit of video on it. So set builder notation. And maybe I'll just do this version. So informally, if I use the set brace and put some stuff inside, the set of X in B such that P of X, this symbol, this notation, represents the set of all objects, let's call them X naught, in the given set B, where this open sentence, P of X, is satisfied. Okay. So, and the actual definition is almost the same thing, but I just have to tell you, well, what are the members of this set? This is how I phrased all my previous definitions. For any object Z, Z is a member of this set if and only if Z is in B and P of Z. Just for emphasis, I'll say P of Z is true. P is some sort of proposition, open sentence that Z can get substituted in for. And you can do the same thing. You don't absolutely have to have the B. Sometimes you'll see just the set of x such that P of x. And then you just do the same thing, but there's no mention of B anymore. All right, in almost every book you read on set theory or proofs or whatever, this notation comes up all over the place, and they use it to define things. So you'll see, as an example, you'll see they'll say, well, A union C is by definition the set of all x, such that x is in A or x is in C. Okay. Or they'll say, to use the thing we've just been talking about, the intersection over I in capital I of, say, B sub I is the set of all x such that there exists an I in I. X is in B sub I. Or just to give you one more, if we had like an interval or something, AB, open on the left, closed on the right, is the set of all x in the reals such that A is less than x is less than or equal to B, and so on. So this is all great. The thing is, when you actually come up with a proof, as we've seen repeatedly here, you don't sort of say it this way. You say, x is in this, and then that changes into that. And so that's why I write my set definitions using sort of the membership notation. But because of this, it ends up being the same thing. I tend to not use the set builder stuff so much compared to other people, but you will definitely see it all over the place. You need to be aware of what it means. If for some reason it causes a lot of confusion, if you just start by saying this and this and this to your definition, and you ask someone to prove something, they can't really deal with the extra. It takes a while to get used to the extra level of translation compared to just saying X is a member of this if and only if this or that. All right, but I think my video is already a little long, so let's stop the lesson right there and see you next time. Take care.